The idea involved in adding and subtracting fractions makes good sense if we realize that a fraction is composed of a numerator and denominator, and the numerator tells how many things we have and the denominator tells how big those things are. So when we're bringing fractions together, then we have this many items of that size, and we're adding this many items of that same size. And since we're adding items of the same size, we can accumulate them by simply adding numerators. So the general idea is that to add and subtract fractions, we need common denominators, and we simply add or subtract numerators. So this really is 3 plus 1/5 or 4/5 for the result. Now, it doesn't make any difference the circumstances involved in the collection of fractions. It's the idea that if we have a common denominator, we bring the fractions together by collecting numerators. This is 4 plus 3 over n. So it's like this, and we don't always write this step. When we see that we have a common denominator, we simply collect those numerators, and in this case, we find the answer to be 7 over n. All right, so that's the idea. Now, when the denominators are not alike, we're trying to bring together items that are of different sizes. And we can't describe with a single fraction a number and a size here corresponding with two different sizes, you see. So it's the idea that we have to change into a common denominator before we're able to bring the fractions together. And that's what we do as a first order of business. We identify a common denominator, change the fractions into that common denominator, and then collect the fractions. Now, a common denominator is a common multiple of these denominators. And generally, it's easier, and the fractions are simpler, if we can identify the least common denominator for the two fractions, which is the least common multiple for the two denominators. Now, in numbers like 8 and 16, it's pretty easy to identify the least common multiple of these. And a way of doing it is to kind of request to yourself, kind of like this: what's the smallest number that both 8 and 16 will go into a whole number of times? That's the least common multiple, you see. So, and that number turns out to be 16. 16 is the least common multiple for 8 and 16. So we're changing into new fractions whose denominator, excuse me a moment, is 16. So we'll rewrite like this. Now, one of them is kind of trivial, but at any rate, we would write the common denominator like this, and then we'd say 8 into 16 goes 2, and then 2 times 3 is 6. And by saying 8 into 16, we're just identifying the number that's multiplied in the denominator to get this new denominator, and we're going to multiply the same number in this numerator to get the new numerator. So 8 into 16, 2, 2 times 3, 6. And then for this one, it's trivial. We just bring down 3/16. Now that we have common denominators, we bring the fractions together by adding numerators. So 6 plus 3, 9. This is 9/16 for the answer. Similar thing here. We have 5, 6 plus 3/8. We need a common denominator. The common denominator is the least common multiple for these two. There are a couple of ways of finding that least common multiple. Now, in the past, when we talked about least common multiples, we identified the least common multiple by looking at a prime factorization. And I want to show you that method here, but I want to talk to you about alternate methods, because some students find it easier to look at problems like this one way, and some find it easier another way. And I want to show some alternate methods here. But 6 is 2 times 3, so we would be thinking this, and 8 is 2 times 2 times 2, or 2 cubed. Now remember, when we were looking at prime factorizations before and identifying a least common multiple, the least common multiple contains every different factor that we see the most number of times that we see them. So the least common multiple would contain a 2 and a 3, and the 2 is here, but it occurs 3 times. So the least common multiple is 2 cubed times 3. That's 8 times 3, or 24. So our common denominator is 24, and we're changing into that common denominator for the two fractions. Now, another way to look at it is like this. The other way is to say, what's the smallest number that both 6 and 8 will go into a whole number of times. And to make that discovery, sometimes it's easier just to take the larger of the two denominators and think about multiples of that. And ask yourself if this other one will go into any of those multiples. For example, 8 times 2 is 16. Does 6 go into 16? No. 8 times 3 is 24. Does 6 go into 24? Yes. So 24 is a multiple of 8. 6 goes into that 24, so 24 is also a multiple of 6. So that's just another way of looking at it. 6 into 24, 4. 4 times 5, 20. So this is 20 24ths. 8 into 24, 3. 3 times 3, 9. Now we're adding the numerators, 20 plus 9, 29 over 24ths. And usually we change improper fractions into mixed numbers. We say 24 goes into 29 one time with 5 left over. So it's 1 and 5 24ths for the mixed number. Here we have one of the fractions has a different sign. Here we have negative 3/8 and plus 5/8. And notice the denominators are the same. We have common denominators. So all we need to do is bring together those numerators. And we think of this as negative 3 over 8 plus 5 over 8. That's one way to do it. We could think of this as a subtraction. Just shift this one over here and have 5/8 minus 3/8. You see, now we have a subtraction problem. But we could think of a collection problem like this, and they're equivalent to one another, it turns out. But collecting numerators here, negative 3 with 5, from before, we know that the answer is 2, and it's 2/8, which reduces to 1/4. Here again, same idea. We have negative 7/8 plus 3/8. We think of this probably as negative 7 over 8. You see, and this is 3/8. And we're collecting negative 7 with 3. Well, negative 7 with 3, the signs are different. It's kind of like this. We're thinking of it as, whoops, my bad. We're thinking of it as negative 7 plus 3 over 8. You see, and negative with positive, oh, the signs are different, so we subtract digits and attach the sign of the larger of the two. And so we take 3 from 7 to get 4, and we attach the sign of the larger of these two. 7 is bigger than 3, so the sign on 7 is negative. It's negative 4/8 or negative 4/8 like this. But whether we look at it as negative 4 over 8 or negative 4/8, it reduces down to negative 1/2 as the final answer. All right, here's one. Again, two different signs, but the denominators are not alike. We need a common denominator just to start the whole situation, and that common denominator is the least common multiple for 6 and 4. We know that to be 12, so we're going to change this into so many 12ths, and we're going to change this into so many 12ths. Now, 6 into 12 goes 2. 2 times 5 is 10. And this minus sign can float, you know, and I'm allowing it to float to the numerator for collection purposes. 4 into 12 goes 3. 3 times 3, 9. Now we have negative 10 with positive 9. Negative 10 plus 9, you see, or negative 1/12. And we can write it as negative 1/12 with the minus sign as the sign of the numerator or as the sign of the fraction itself. Generally, it's a little more acceptable to write that minus sign as the sign of the fraction. Well, here we are collecting a couple of negatives, and I can write it like this, or we saw when we were dealing with integers that this can become negative 2/3 minus 4/5. These are equivalent to one another. Subtraction is the same as adding the opposite. We can think of going from here to that, but it's a little simpler, I think, to leave it like this because we don't have the parenthesis to deal with and we don't have two signs preceding a fraction or a number. And so we're simply collecting a couple of negatives here, and that's all there is to it. I think that's the best way to look at it. Common denominator is 15. Let's see, 3 into 15, 5. 5 times 2, 10. So this is negative 10/15. And again, this minus sign, gee, we can leave it as a sign of the fraction. We can cause it to move into that numerator, and it's okay. There are just a lot of ways of looking at this. 5 into 15 goes 3. 3 times 4, 12. And I can think of it like this, or I could think of it like this. You see, and that's okay. That sign right here can float into either of these two positions. But either way you look at it, however you think your way through it, it's going to turn out that you're collecting a negative 10 with a negative 12. And you're doing that whether you think of it like this or whether you think of it like this. And even this sign can be here, and you still think of it as negative 10/15. You think of the negative sign going with that numerator, and this minus sign going with that numerator for collection purposes. All right, so the negative 10 with a negative 12 is negative 22, so it's negative 22/15. And as a mixed number, it's negative, let's see, 15 into 22 goes one time with 7 left over. So it's 1 and 7/15, and the whole mixed number is negative. Here we're adding a whole number with a mixed number, and you recall from before, from arithmetic, what needs to be done in this circumstance. You could align these vertically if you wanted to and add whole numbers with whole numbers and fractions with fractions. Another way to look at it if we're talking horizontally is like this. This is really 3 plus 2 plus 4/5. You see the 2 and 4/5, you read it like that, 2 and 4/5 can be 2 and 4/5 like this. So here we're thinking of it kind of like that. Then we can reassociate like this, you see, plus 4/5, and we add the whole numbers to get 5 and 4/5, which we would write like this as a mixed number. So 5 and 4/5. We could come directly to an answer just from right up here, just by understanding that we're collecting the whole numbers together. And here, similar idea. We are collecting whole numbers with whole numbers, fractions with fractions. And in arithmetic, you would arrange this problem kind of like this probably. Remember this from arithmetic? You would write 3 and 5/8 plus 4 and 7/12. You see, and you do this. Oh, we don't have a common denominator, so we go over to the side and we find a common denominator between 12 and 8, 24. So let's see, we would think 8 into 24, 3, 3 times 5, 15, 12 into 24, 2, 2 times 7, 14. And now whole numbers with one another give 7. 15 and 14, 29 over 24. So now notice that we have a whole numbered part and an improper fraction right here. And it turns out that we change this into a more acceptable mixed number by thinking of this as 7 plus, and this 29 over 24 is really, let's see, what mixed number? 24 into 29 goes 1 with 5 left over. So it's 1 and 5 over 24. You see, and the whole numbered part is collected with the 7 to give 8 and 5/24. Well, that's a lot to keep straight here in this form, and it's a lot to keep straight over here as well. But just realize that what's happening over here is 3 plus 4, 7. And then think about adding the fractional parts. That is, think about what it means to have 5/8 plus 7/12. You see, and then the common denominator, as we found earlier, is 24. 8 into 24, 3, 3 times 5, 15, 12 into 24, 2, 2 times 7, 14, and now add those numerators and we get 29, whoops, not equals, plus 15 and 14, 29, so 29 24ths, and this becomes 1 and 5 24ths, and collecting the whole numbered parts we get 8 and 5 24ths as expected. Here's a rather interesting one, and the numbers are rather large, and I want to show you actually a couple of ways of working the problem. First, let's think about finding a common denominator. All right, now if we're thinking common denominator, we might be thinking, well, since the numbers are pretty big, we might think about a prime factorization here. And let's see, for 35, the prime factorization is 5 times 7. And for 42, 42 is 6 times 7, but 6 is 2 times 3. So this is 2 times 3 times 7. Now, I'm showing you this particular method and this way of setting the problem up because this is the way that this is the format that we're going to use when we get to some higher algebra, it turns out. That when problems get more complicated, we use this factored form to identify common denominators and all of that kind of thing. Now, the common denominator needs to contain every factor that we see here the most number of times that we see it. Remember, for least common multiple, and that's what we're looking for here. So the common denominator contains, well, let's identify that common denominator. And I'm going to do it out to the side. And I'm doing it out to the side because this is the way we're going to deal with the situation when we get into some higher level of algebra. The common denominator contains every different factor that we see. We see a 5, we see a 7, we see a 2, we see a 3, we see a 7. Now 7 appears twice here, but 7 appears the most number of times that it appears in any prime factorization is only once. So it's going to appear only once as in our common denominator or our least common multiple. So the least common multiple will contain, and I'm going to write the factors kind of in numerical order. The lowest factor, the smallest one, is 2. The next largest one is 3. The next largest one is 5. The next largest one is 7. Now this product is my least common multiple, which is the common denominator for those two. I don't care what the number is so very much. I can write the number, I can multiply these out and find the number, but I really don't care what it is, but I do care about what factors are in it. Now, compare this least common multiple in factored form with the factors that appear here and the factors that appear here. Now, I want to make that comparison because when I transform these fractions into new fractions that have this as the common denominator, all I'm doing is injecting factors into the denominators and therefore into the numerators. For example, here's what I'm thinking. I need to change this into that or I need to have these factors involved. I have 5 times 7, but so I've got the 5 and the 7 factor. I need the 2 and the 3 factors. So what I'm going to do is multiply in 2 times 3. But if I multiply 2 times 3 into that denominator, I have to multiply the 2 times 3 into the numerator. So it's this idea, you see, and then this is just 25. So in the next step then, I've got 6 times 25, you see, and that turns out to be 150. Over my common denominator. I'm going to leave the common denominator in factored form. And I'll tell you why in just a minute. Okay, now let's go through the same idea over here. Now this is really 30 over this prime factorization. What factor is missing from this prime factorization? We compare over here and we're missing the 5 factor. Okay, so we go back over here and we inject that 5 factor into that denominator. But if we inject it into the denominator, we need to also multiply it into the numerator. So 5 times 30 is 150. Over the common denominator. Now, I have multiplied out numerators, but I've left the denominators in factored form. And there's very good reason for that. The reason we multiply out the numerators is because we end up adding the numbers that are in these numerators. You see, we bring those together. We add them or subtract them when it comes to subtraction. But we're going to manipulate those numbers with addition or subtraction. So we need to have a form which is already multiplied out. It's 5 times 30. It's 6 times 25. You see, now we can add those numerators. So we add 150 and 150 to get 300. Now we're leaving the denominator in a factored form because it isn't changing here as we add or subtract later. And we need those factors in order to see cancellation opportunities. So let's leave this in factored form. By the way, I want to drop this down just a little bit. I want to write it down here as 300 over 2 times 3 times 5 times 7. And again, I could multiply this out, but it's really easy to see the cancellations if I leave it in factored form. Here's what I mean. 2 is a factor in 300. I know that because 2 goes into 300 a whole number of times. And I can say 2 into 2 goes 1, 2 into 300 goes 150. Now, I could have rewritten this as 2 times 150 and cancel the 2's, but it's real easy to do it this way. Now I see that 3 goes into 150. You see, because 3 divides the digit sum here. Remember, 3 into 3, 1, 3 into 150. Let's see, 3 into 15 goes 5. So we have 3 into 150 goes 50 times. Oh, 5 goes into 50. So 5 into 5, 1, 5 into 50 goes 10. I'll just put that out here. Now, what's left when the smoke clears here? Well, we have 10 for the numerator and 7 for the denominator. This is 10 sevenths, or it is 1 3/7 for the final answer. Now, you may be thinking, well, gee, you know, this problem involves such big numbers to begin with. I wonder, because we had so many cancellation opportunities at the end of the problem, if it's not the case that we could have canceled at the beginning of the problem. That would have been a pretty good thing for us to kind of look for, wouldn't it? Because we went through a lot of business with some rather large numbers in this process. And it does turn out that we could have reduced the problem from the very beginning. It turns out that 25 over 35 can be reduced like this. 25 has a 5 factor in it, 35 has a 5 factor in it. So we could say 25 divided by 5 is 5, 35 divided by 5 is 7. Or we could say 5 into 25 goes 5, 5 into 35 goes 7. But at any rate, it reduces to 5/7. And in a similar way, this rascal reduces as well. 6 divides both the numerator and denominator. 6 into 30 goes 5, 6 into 42 goes 7. So we have 5/7 and 5/7, a common denominator. All we have to do is add numerators. So this becomes 10/7 or 1 3/7 as we found earlier. Suppose we want to evaluate x plus y when x is this mixed number and y is this other mixed number. Well, all we do is kind of follow our nose through it as we have done in the past. You write down the expression that we want to evaluate. Then we replace letters with numbers. X has the value 2 3/4. Y has the value 7 5/6. Now we need a common denominator for the fractional parts. We know that the whole numbered parts are just going to come directly together. 2 and 7 give us 9, but the challenge is the 3/4 plus 5/6. Now I'm just writing this again for emphasis, but it's a notion that we need a common denominator, and that common denominator is the least common multiple for 4 and 6. Turns out to be 12. So this is 9 plus so many 12ths plus so many 12ths. Now 4 into 12, 3, 3 times 3, 9, 6 into 12, 2, 2 times 5, 10. And now we're collecting those fractions by adding the numerators. 9 plus 10, that's 19. So this is 19/12. But 19/12 is an improper fraction. It turns out to be, well, let's see. Oh, I'll keep writing those equal signs, don't I? I can't wait to get to equations. Plus 12 into 19 goes 1 with 7 left over, so it's 1 7/12. And the 1 adds with the 9 to become 10 7/12 for the evaluation of the expression. The general idea in subtracting fractions and mixed numbers is exactly the same as the general idea in adding. We need common denominators, and we simply bring together numerators. Consider a few examples. 4/5 minus 1/5. We have 4 of these things. We're taking away 1 of the same sized items. So 4 of these things minus 1, that gives us 3 of these same things. The general idea is that we're just subtracting numerators and we retain that common denominator, so we get 3/5 for the result. We probably wouldn't write this step. When the denominators are not alike, we need to rearrange the fractions as before and write these in terms of a common denominator. Common denominator is the least common multiple of 12 and 8. And once again, we can kind of take the larger of these two and imagine multiples and then ask ourselves if the other denominator goes into the multiples of this one. Now, 12 times 2 is 24, and it does turn out that 8 goes into 24. So 24 is the common denominator, and we'll rewrite then as, well, let's see. 12 into 24, 2. 2 times 5, 10. 8 into 24, 3. 3 times 3, 9. 10 24ths minus 9 24ths is 10 minus 9, 1 24th for the answer. Here we have two fractions. We can think of, gee, this one is negative and we're subtracting this other one, or we can think of them as both negatives. We have the same little tricky situation that we had when we were dealing with collecting integers before. Remember, subtracting is the same thing as adding the opposite, and so we go through this idea of, although this is subtract 5/12, we can think of this as plus negative 5/12, and if we see through that, we can think of this as negative 5/12. We think of this as negative 2/9. We're just bringing together a couple of negatives. You see, so all we need to do is think about these signs applied to those numerators and just bring those together as we understand the situation. Now, we need common denominators here, and I should have mentioned that perhaps before, but the common denominator among 9 and 12, gee, I'm thinking about multiples of 12, turns out to be 36 is the common denominator. 9 into 36 goes 4. 4 times 2, 8. So this is negative 8/36. Minus 12 into 36 goes 3. 3 times 5, 15. So it's negative 8 with negative 15. You see these minus signs just kind of go with the numbers in the numerators. And negative 8 with negative 15. Signs are the same. Add those numbers, add the digits, and attach the common sign, which is negative. So 8 and 15, 23. So we have 23/36, and it's negative, and we would put the sign as the sign of the fraction. It could be the sign of the numerator, but we usually write an answer like this with the sign, a minus sign as the sign of the fraction itself. When we have a minus-minus situation, just as we saw with integers, it turns out that this is the opposite of negative 5/4, or it's plus 5/4. Or we could say it's negative understood 1 times negative 4/5. Negative times negative, positive. So anyway you look at it, it's 2/3 plus 4/5. Now I've taken care of that sign situation, but in order to bring the fractions together, I need a common denominator. The common denominator is 15. 3 into 15, 5. 5 times 2, 10. And then 5 into 15, 3. 3 times 4, 12. 10 and 12 is 22, so this is 22/15. And 15 goes into 22 one time with 7 left over, so it's 1 and 7/15 as the mixed number answer. This problem says to find the difference between 5 and 8/9 and 2 and 5/6. Difference implies the answer in a subtraction problem, so we're going to subtract. And when the word difference is used, we take the first item and subtract the second one. So what we're doing is taking this number and subtracting that one. Now it doesn't matter whether we set this problem up horizontally or vertically. Some students find it easier to set this up vertically, especially when the mixed numbers turn out to, or when we're subtracting with mixed numbers, because sometimes borrowing is necessary in that situation. I don't know if it's necessary in this situation, but sometimes it's necessary. But this is what we're doing. We need a common denominator now, so we'll go over a step over here and identify the common denominator as, well, let's see, between 9 and 6. 9 times 2 is 18. Does 6 go into 18? Yes, it does. So 18 is the common denominator. 9 into 18, 2. 2 times 8, 16. And then 6 into 18, 3. 3 times 5, 15. And now we're subtracting. Now remember, we think of the whole numbers subtracted from one another and the fractions subtracted from one another as sort of separate events here. And generally it's better to think about the fraction subtraction first, because the borrowing might be necessary. We'll see that, I think, in the next problem. 16/18 minus 15/18. 16 minus 15 is 1, so this is 1/18 for the fractional part. And then 5 minus 2 is 3 for the whole numbered part, 3 and 1/18. Here's a situation that involves this borrowing, which I referred to. Now notice that we have common denominators already. We want to kind of bring these together. I think I want to rewrite these to give myself a little more room to work out to the right. Let me just come down here and repeat the problem. I should have thought about that when I loaded this board a little earlier. Okay, so here's what we're doing. We have a little more room out here to the right. Now, we're thinking about whole numbers from whole numbers, fractions from fractions. We can't take 3/5 away from 1/5. Now, I know that we have available to us signed numbers. We talk about negative values. If we take 1/5 minus 3/5, we could think of this as negative 3/5. But look at this. We have a number up here which is larger than the number down here. So it should make some sense that the answer here is going to be positive. And we don't want to have a positive whole number part and a negative, you see, fractional part. We'd like for those to be consistent with one another. So at any rate, we end up borrowing here. We don't have enough fifths to take 3/5 away. So we're going to borrow from the 4. We're borrowing 1 from the 4, leaving 3, and the 1 that we borrow is really 5/5. So 5/5 with 1/5 gives us 6/5. Now let me say that again. This may be the first time we've talked about this in this course, but we're borrowing from the 4. So we take 1 from the 4, and that 1 that we borrow is really 5/5. And we take the 5/5 that we borrowed from the 4 and we add it to the 1/5, you see, and that's where we get this 6/5. And the 1 that we borrow from the 4 leaves 3 for the whole numbered part. All right, now we can subtract 2 and 3/5 because we have enough fifths to take away from. You see, we have 6/5 minus 3/5. Oh, that leaves 3/5. And 3 minus 2 is 1. So 1 and 3/5 for the result of our difference, or finding this difference. Now, here's one that's set up horizontally. If we want to stay with that horizontal configuration, that's okay. First order of business might be to find a common denominator. We're not sure, perhaps, right at this point whether or not we need to borrow, but we'll be able to tell once we find the common denominator. Common denominator between 8 and 6 is 24. So this is 9 and so many 24ths. And we're going to subtract 2 and so many 24ths. Let's find out how many of each. 8 into 24, 3. 3 times 1, 3. And then 6 into 24, 4. 4 times 5, 20. So now we're subtracting. Now we're trying to take, now generally speaking, this number is smaller than that number. They're both mixed numbers, but this is a bit over 2 and this is a bit over 9. And certainly we get a positive result when the subtraction takes place. So we don't want a negative for the fractional part. And 3 24ths minus 20 24ths, no, we can't do that. We need more 24ths over here. So we find those other 24ths by borrowing from the 9. We borrow 1 from the 9, leaving 8. The one that we borrow is 24 24ths. Adding 3 24ths, we get 27 24ths. And now we're ready to go with the subtraction. For the fractional part, 27 24ths minus 20 24ths is 27 minus 20. 27 minus 20, that's 7. So 7 24ths for the fractional part. Then for the whole numbers, 8 minus 2, 6. 6 and 7 24ths. Here's one where we don't have a fraction as part of this first number. This is not a mixed number, is it? It's just a whole number, and we're subtracting a mixed number. Now, we can set this up a lot of different ways. You may be more familiar with it set up like this. 7 minus 2 and 3/8. And it's okay if you want to rewrite it like this. It's perfectly all right. Now, we need some eighths up here to subtract from, and so we borrow from the 7, leaving 6. And the one that we borrow is really 8/8. Now notice I'm expressing as 8/8 in order to conform to the common denominator of 8 that we have in the other part of the problem. So we're subtracting, let's see, 2 and 3/8, and away we go. 8/8 minus 3/8 is 5/8, and 6 minus 2 is 4. So 4 and 5/8 is our answer. Here's one where we're asked to discover whether or not, or to tell whether 3/8 is a solution of this equation. If it is, then it's a replacement for the letter that makes the statement true. And so we'll simply rewrite the equation and replace the letter with this candidate as a solution. So we have 3/8 minus 5/6. And we will collect on the right. Now let's see. We need a common denominator. The common denominator looks like it's 24. So let's see. We have 8 into 24, 3. 3 times 3, 9. 6 into 24 goes 4. 4 times 5, 20. 9 minus 20 is negative 11. So 2/3 over here, negative 11 24ths. Are these the same? No, they're not the same. These aren't equal to one another. So this value does not make the statement of equality